Okay, so we're going to go over the conceptual exercises. These are not very hard. They can all be found in the reading part of your unit right here, okay? Like I said, these are pretty simple, but we'll go through them anyway. So, number one, which force, gravitational or electrical, repels as well as attracts? So, read in the reading material, two objects with like charges, in other words, the same charges are but close to each other, they experience a repulsive force. Repulsive means like push away from each other, so that's like repel, right? And then if they have different charges, they attract. So positive and negative attract, positive and positive repel, okay? Or negative and negative repel. So in that case, this is electrical. Okay, number two, gravitational forces depend on the property called mass. What comparable property underlies electrical forces? So in other words, you're looking at your formula, right? What is the similar property of mass in the electrostatic force formula? Well, it's charge, right? It's Q. So that one's easy, okay? That one's easy. So number three, how do protons and electrons differ in their electrical charge? Okay, proton, positive, proton, positive. Protons are positive. Electrons, opposite of that, negative, right? And then neutrons have no charge. So neutrons are neutral. So just to remember that. Okay, number four. And if you guys know these, just stop the video and do it on your own, because sometimes it feels good to, get it right on your own rather than have the answers read. Number four, is an electron in a hydrogen atom the same as an electron in a uranium atom? So hydrogen has one proton. Its atomic number is 1. Uranium is really, really big, right? It's a very heavy one. But the answer is yes. Electrons are the same, whether they're in hydrogen or uranium. The only difference is one has a lot more electrons than the other. Hydrogen only has 1, uranium has quite a bit more. Nevertheless, electrons are all the same. Cool. Number 5. Number 5 and 5A and 5B are pretty much the same as 3, right? So 5A, how do like charges behave? In other words, same charges, like plus plus or minus minus. Like charges repel each other. B, how do unlike charges behave? You ever heard that term opposites attract? So opposite charges attract each other, right? Okay, let's look at 6. If electrons are rubbed from a cat's fur onto a rubber rod, the rod became positively or negatively charged. So we got to think about this. If it says the electrons are rubbed from a cat's fur to the rod, so that means the rod is gaining electrons, which is, electrons are negative, right? It's gaining negativity. So does the rod become positive or negatively charged? Well, it becomes negatively charged, right? Because the rod is gaining electrons. If you gain negative, you're becoming negatively charged. How about the cat's fur? The cat's fur becomes positively charged. That's B. So remember, you don't transfer protons, okay? You transfer electrons to become negative or to become positive. So in other words, if I gain electrons, I become negative. If I lose electrons, I become positive. But there's never a transfer of protons. There's only a gain or loss of electrons, okay? So let's keep going. Oh, did I not have that in the picture? Okay, cool. So there you go. There's that one. So let's go to the back. Okay, so what does it meant to say that a charge is conserved? This is the same thing as like conservation of energy. A charge is conserved. It means there's no charge created or destroyed. It's just transferred from one object to another. All right, so that's what it means to have a charge conserved. Okay, so let's look at 8A. How is Coulomb's law similar to Newton's law of gravity? So let's pull that back up. These are the two laws. So how is Coulomb's law similar to Newton's law of gravity? Well, both forces are inversely proportional to the distance squared, so that's how they're similar. So notice that this is the force of gravity, this is the electrostatic force. they are inversely proportionate to the distance squared, meaning if you increase the distance, the force will drop considerably, right? All right, let's look at B. How are the two laws different? Well, remember, gravity, the force of gravity only attracts, whereas the electrostatic force, Coulomb's law, will repel also, kind of dependent on if it's positive or negative, right? Okay, let's look at number 9. The SI unit of mass is the kilogram. What is the SI unit of charge? Well, again, this is in the reading. So if we check that out, and really, it's really small reading, so a lot of this should be pretty simple. The symbol for the electrical charge is letter Q, and the SI unit for charge is the Coulomb, right? So that's easy. So C, Coulomb, that's our answer. Piece of cake. Okay, let's move on to 10. See, this stuff's actually pretty easy. It looks kind of scary, but it's not. What is the difference between a good conductor and a good insulator? Okay, so remember, a conductor just lets electricity flow, meaning it lets electrons flow. Right? So a good conductor has outer electrons that are free to move. You know, they're free to be traded, right? A good insulator has outer electrons that are tightly bound to the atom, meaning they don't want to move. In other words, it does not allow current to go through, like rubber. Rubber does not, electrons in rubber do not want to move. They're very tightly bound, so that means it's a good insulator. It keeps that electricity from flowing through it. Whereas copper has very loose electrons, man, they're ready to party. You give them something to jump on and they're going, right? So that's the difference. That's number 10. Remember, that has 2 answers, okay? All right. Number 11 is kind of just a piggyback on number 10. Why are metals good conductors? Well, again, their outer electrons are they're ready to rock. They're loose, you could say. They are ready to jump ship and go somewhere else. So that's why they're good conductors. Their electrons are ready to rock. Why are materials such as rubber and glass good insulators? Well, that's B. Their outer electrons are not really free to move around. They don't want to move. They're stuck where they're at. Meaning when something is trying to push electricity through, these electrons don't want to move. And if you remember, a current is kind of like a flow of a conga line, right? Where everybody's in line and everybody's moving. If one part of the line just stops and refuses to move, then you can't have people flowing through that part, meaning there's not going to be any electrical current, right? That's like an insulator, okay? So, is that it? Yeah, that's it. So here's the reading. Very short reading. Hopefully you guys got that. Pretty easy stuff. There you go. If you guys got questions, let me know.